Okay, so we've talked about what forces are. We've talked about Newton's first law, which kind of gives us a little window into what forces do. Let's talk about some of the forces we're going to encounter in this semester. First up, weight. Weight is the force of gravity acting on the object. If I hold this little piece of wood in my hand, then I can feel the gravity pulling on it. I can feel that pull down on my hand. Gravity pulling on this, that's the weight force. So weight is a force, and it is the gravity acting on the object. Now we have to be a little bit careful, because weight is closely related to, but not the same as, mass, right? Mass is how much stuff. So thinking about this little wooden toy that I have here, again, weight is the force of gravity acting on that. That's what I feel when I hold it here, right? But mass is how much stuff there is in here. In a way, it's like counting all of the protons, neutrons, and electrons that exist in here. There'd be some unit conversions you'd have to deal with there. But that's basically what we're doing when we say how much stuff, how many protons, neutrons, and electrons are in this object. And that's mass, right? So mass is how much stuff. Weight is the force of gravity on that stuff. They're related with a very straightforward equation. W equals m times g. Now this g is what we learned a few segments ago. 9.8 meters per second squared. That's what g is, only near the surface of the Earth. So you can see here that weight changes depending on what g is. Mass does not change, right? So if I were to take this little wooden toy out into the middle of space, far from any stars or planets or anything that might cause there to be some gravity, what would its weight be? 0. But guess what? Its mass would be identical because it still has the same amount of stuff. So its mass would not be 0, but its weight would be. If I took it to the moon, where gravity is approximately 1/6 as strong as it is here on Earth, then I'd find that its weight was about 1/6 what it is here on Earth, but its mass was exactly the same. Weight is measured in newtons because it's a force, and mass is measured in kilograms. So they have different units. Now, I mentioned in the previous segment that newtons and pounds are equivalent. So in the English system, we measure forces in pounds. The unit in the English system for mass is one you may not have encountered before. It is the slug. One measures mass in slugs if one is an engineer in the United States of America. Okay, moving on. A spring can exert a force. We probably knew that. I've got this spring here. If I stretch it, I can feel the force pulling on my hand. The farther I stretch it, the greater the force. Ooh, that's really hard. Great. More on that in a couple chapters. Tension. Tension is the force that a rope exerts on an object. And tension can only pull. You show me a rope that can push, and I will show you a stick. So tension, we use a T to represent tension, a capital T. And it is the force that a rope exerts, again. So in this case, we see a sled being pulled by a rope. It is the tension force that is exerted on the sled. The normal force can be a little bit surprising. Let's say I've got some surface here. I've got this clipboard, and I place my wooden toy on that surface. Well, what is the acceleration of this wooden toy? 0. Its motion is not changing. So what forces are acting on it? Well, definitely gravity, for sure. And if it's not accelerating, there must be some other force acting on it. What force is it? Well, it turns out there's a force from this surface pushing up, right? And you could say, oh, well, it's not falling because the clipboard's in the way. Oh, you're not wrong. That's completely right. It's just, that's not a way of thinking about this that we can go anywhere with, right? This idea of this abstraction that we're using of forces, it doesn't change the reality, right? We all agree that this is just sitting here and it's not going anywhere because the surface is in the way. And certainly if I move that surface, then it falls, right? Okay, so we all agree on that. This idea of forces is just an abstraction that helps us to understand it, and in a very specific way. It helps us to understand it mathematically, right? And so this idea that, oh, it's not falling, its motion isn't changing because the clipboard's in the way, that's fine, but we can't build a skyscraper or design a rocket using that idea, right? So instead we say, hey, the gravity is pulling down, that's a force, and there's another force pushing up, that's the force from the surface. We're going to call that the normal force. Now we have to be a little bit careful calling it the normal force, because in everyday language, the normal force, or normal, that word means just everyday, usual, typical. And so a lot of times students take that to mean that every object has a normal force on it. Oh, it's normal, every object has it. That's not what we mean. In this context, we mean the mathematical definition of normal. And the mathematical definition of normal means perpendicular to. And so in this case, the normal force is always perpendicular to the surface. If we looked at a side view, the force would be pointing straight out that way if this is on there like this, right? So the normal force points straight up away from the surface, perpendicular to the surface. That's what normal means in this context, is perpendicular. And we can think about that as really, it's almost like a spring force. If we were to imagine the molecules that make up that surface, they're being held together with something. We can imagine those molecular bonds as being like little springs, and those little springs get stretched just a tiny bit when I place an object on there. Okay, so we could imagine it like that, but either way, it's the normal force, and it is always perpendicular to the surface. It doesn't always have to be up either. You know, if I come along and I push on my chalkboard in this direction, well, I'm pushing in this direction. It turns out the chalkboard is exerting a normal force on my hand. It is normal to, or perpendicular to, the surface. So in this case, the normal force is pointing in this direction. Moving along. Friction. We've got static friction and kinetic friction. Well, if you rub your hands together, you can feel the friction between those two surfaces. If you slam on your brakes and you're sliding across the pavement, then there's friction between your wheels and that in the surface of the road. So you've encountered friction a lot in your life. In this class, we're going to distinguish between static friction and kinetic friction. And so static friction exists when the two surfaces are not moving with respect to each other. In other words, when there is no sliding happening, then that is static friction. If there is sliding happening, then that is kinetic friction. And so here again, here is my piece of my wooden toy on my clipboard, and I can give this a little tilt, and you can see that my wooden block is not moving. It's not moving because there's a friction force that is holding it, that is preventing it from sliding down this tray. Which friction force, static or kinetic? In this case, it's static because there's no slippage between the two surfaces. It's not slipping. If I tilt it a little bit more, it started to slide. As it was sliding, there's still friction, but since there's motion there, it's kinetic friction and not static friction because there's sliding between the surfaces. Interactions with the air. We kind of break these into two categories, drag and thrust. If you've ever stuck your hand out the window when you're going 60 miles an hour down the highway, you felt air pushing on your hand. That was wind resistance you were feeling. We're going to call that drag in this class. So that is drag. But you know what? Drag can happen in any fluid. So it would be drag that would resist the motion of a submarine moving through water. Or if you put your hand in the water and you went like this, then you would feel drag on your hand. If we're talking about a propulsion kind of a force that's in a fluid, then we call that thrust. And so we could think of thrust created by a rocket or a jet engine or even a propeller would create thrust. And so thrust would be, I'm pushing this way on some air, and so the air is going to push this way on me. We're getting ahead to Newton's third law, but that's the idea of thrust. And that can happen in a number of different kind of contexts. Rocket engines, jet engines, or propellers are the ones I can think of right now. Squid, I guess. A squid sucks in water and then shoots it out in order to propel itself. You could call that thrust as well, because it's propelling a fluid in one direction in order to move in the other direction. And remember, a fluid is anything that flows. So air, water, they're both fluids. We'll talk more about that in chapter 13. Okay, so now we've gone through our laundry list, our catalog of forces that we might encounter this semester. So now we need to learn to identify those forces. And this is a step that hopefully we're going to get pretty good at pretty quick, and we're going to kind of be able to just wrap this in with some other steps. So, by the time we get sort of well into the next chapter, which is also all about forces, we're going to be jumping straight to making our force diagram, our free body diagram. But for right now, we need to learn to identify the forces on an object. Here's a list of steps. This is directly from your text. First, we need to identify the object of interest. Recall that every force has an object and an agent. The agent is the thing that's causing the force, and the object is the thing that the force is on. The object is the object of interest. We need to identify which object is it we're talking about, because forces always exist on an object, right? With no object, there's no forces. Okay, draw a picture of the situation. Show that the object of interest, show the object of interest and all the other objects, such as ropes, springs, and surfaces that touch it. Then you're going to draw a closed curve around the object. Only the object of interest is inside the curve, everything else is outside. And then everywhere on the boundary of the curve, where the object touches other objects, then where the object of interest, I should say, touches other objects. Anywhere where that happens, there's a contact force. So we should identify what those contact forces are. And we should label them using those standard labels that we saw in the previous few slides. And then we should also take a minute and say, are there any long-range forces? There's only, depending on how you count, 4 or 5 long-range forces in the universe that we know of. Gravity. We're going to talk a lot about that this semester. In fact, that's the only long-range force we're going to talk about this semester. So we've got gravity, aka weight. And then we also have the electric force, the magnetic force, the weak force, and the strong force. Now, at this point, due to the work of, people like Maxwell and Einstein, it turns out that the electric and the magnetic forces are now recognized as being two sides of the same coin. And so we call that the electromagnetic force. And so really, in this universe, as far as we know at this point in history, we know of 4 long-range forces. Gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. The strong nuclear force is what holds protons and neutrons together within the nucleus, and the weak nuclear force has to do with holding together the neutrons and the protons themselves. The only one of those we're going to talk about this semester is weight. Okay, moving on, let's practice doing this. Here's an example. A block is dragged uphill by a rope. Identify all the forces acting on the block. Why don't you try this on your own and then hit play on the video and see how close you can. Let's do a quick picture. There's my block and my rope on a hill. Great. What is my object of interest? It says, identify all forces acting on the block. So the block is my object of interest. There we go. I drew a closed curve around my object of interest. Identify the forces that exist, the contact forces that exist everywhere where that closed curve touches other objects. Well, right here, we've got the object interacting with this surface. What forces would we have there? Well, we know that there's the normal force that's always perpendicular to a surface, that's keeping this block from plummeting through the surface towards the center of the Earth. We call that little n normal force. Well, it didn't tell us it's a frictionless surface, so presumably there's also friction. Is it static friction or kinetic friction? Well, it's being dragged, so it is sliding. Therefore, that is kinetic friction. The other place where we see an object interacting with the object of interest is right here. The closed curve crosses my rope. What kind of force do ropes apply? Tension. And our standard symbol is a capital T. Okay, there we go. We have identified all of the contact forces. Are there any other forces? Well, we're going to assume that this is on Earth, or Mars, I guess. In which case, we definitely have weight. Let's include that. It is a long-range force. Okay. Block A hangs from the ceiling by a rope. Another block B hangs from A. Identify the forces acting on A. Again, why don't you try this one on your own? Pause the video and see how it went. I'm going to draw a quick picture. There's my quick picture. What is my object of interest? Well, it says identify the forces acting on A. So block A must be my object of interest. Okay, there's my closed curve. Well, let's look at where the curve interacts with objects. Well, we've got it here and here, right? There's only two places, and it's two ropes. And so we should have two tensions. Now, is that the same rope or different rope? Well, those are two different ropes, and so we should have two different tensions. There's no reason to expect that the tension should be the same since they are two different ropes. So let's go ahead and give them different names. I'm going to call this one T1, and I'm going to call this one T2. Those are all the contact forces I can see. Again, there is gravity, right? So it has weight, and let's go ahead and label that weight. Let's be careful, though. Is that the weight of object A or the weight of object B? It's the weight of object A, right? For sure, it's the object A. Now, you might say, well, yeah, but isn't B is pulling on it, too? Let's be careful. Let's be careful. Weight can only act on the object itself, right? So it is true that gravity is pulling on B, and that B pulls on the rope, and that the rope pulls on A. That is true, but we already accounted for that force right here, right? So it's only the weight of object A. That's our only long-range force if our object of interest is object A. Now, I'm not saying there isn't weight on B. There certainly is. There certainly is. But block B is not our object of interest. The weight of block B acts on block B, and I'm not asking you about block B. I'm asking you about block A. Last one. A ball hanging from the ceiling by a string is pulled back and released. Identify the forces acting on it just after its release. Again, why don't you try this one on your own and then catch up with me. First, I'm going to draw a picture. There we go. There's my ball. What's my object of interest? Identify the forces acting on it. What's it? A ball. That's the ball. So the ball is our object of interest. There's my closed curve. Boy. I only see one contact force right here, right? There's only one place where this interacts with another object. And so we just have tension, don't we? What about air resistance or drag? Well, I just released. This is just after it's released. Well, just like if I drop a ball, right? The split second after I let go, it's not going anywhere, right? There's no motion yet. This isn't moving yet either. If it's not moving, there's no wind resistance, there's no drag. So that's it. Any long-range forces? Just wait. Those are all of the forces acting on